You are currently on a rock, a sphere of iron, silicon, and water that is whipping around its star at 67,000 miles per hour. As you read this, you've traveled about 1,100 miles through space. That rock orbits a cosmic furnace, our sun, a nuclear inferno so immense that 1.3 million Earths could fit inside it. Every single second, this star fuses 600 million tons of hydrogen into helium, unleashing more energy than humanity has used in its entire history. It is just one of up to 400 billion stars in our home galaxy, the Milky Way. This galaxy is a colossal, spinning disk of stars, gas, and dust, so vast that a beam of light, the fastest thing in the universe, takes 100,000 years to travel from one edge to the other. At its heart churns a supermassive black hole, Sagittarius A star, a point of infinite density with the mass of 4.3 million suns. But here is the fact that will truly recalibrate your sense of reality. Our entire galaxy, with its 400 billion suns, its countless worlds, and its central monstrous black hole, is nothing. It is a single, glittering grain of sand. The observable universe is the beach, and that beach holds an estimated 2 trillion other grains of sand, 2 trillion other galaxies. This means for every single star in our own Milky Way, there is an entire other galaxy out there. It also means there are more stars in the universe than there are grains of sand on every beach and in every desert on Earth combined. We are adrift in a cosmic sea of near infinite and unimaginable scale. If you find value in exploring these cosmic narratives, hit that like button and subscribe. And as always with our videos, the visuals are here to add context, but they aren't necessary to follow along. Settle in, let us know where you're joining from in the comments, and let's dive in. To begin to understand, we must first abandon familiar units of measurement: miles, kilometers. These are like trying to measure the volume of an ocean with a teaspoon. Instead, astronomers use the fastest thing in the universe as their yardstick: light. A single particle of light, a photon, travels at 186,282 miles per second. In the time it takes for you to blink, a beam of light could circle the entire Earth more than 7 times. A light year is the distance that a beam of light travels in one full year, nearly 6 trillion miles. And our home galaxy, from one glittering edge to the other, is confirmed to be at least 100,000 light years across. This number, 100,000 light years, is the first great wall our intuition crashes against. What does it even mean? Let's try to build a model. If we were to shrink our entire solar system, out to the orbit of Neptune, down to the size of a single American quarter, our galaxy at that same size scale would be the size of the entire continental United States. Our home would be a coin in a country made of other coins. But even this fails to capture the true character of the galaxy. It fails to convey the sheer, crushing emptiness. Let's try another way. Imagine the sun is a single grain of fine sand. At this scale, the nearest star to us, Proxima Centauri, would be another grain of sand located over 4 miles away. To construct a scale model of the Milky Way using this principle, you would have to sprinkle 400 billion grains of sand across an area larger than the state of Texas, with each grain separated from its nearest neighbor by miles of empty space. This is the mind-bending truth of our galactic home. It is not a solid, crowded city of stars. It is an immense, swirling structure of near-perfect vacuum, punctuated by fantastically isolated islands of matter. We live inside this structure, embedded within one of its great spiral arms. Our cosmic address is in a minor branch called the Orion Spur, a relatively peaceful suburban street nestled between the much larger and busier Sagittarius and Perseus arms. From our vantage point, roughly 26,000 light-years from the galactic center, we have a spectacular view of the cosmic drama unfolding around us. We can see stellar nurseries, vast clouds of gas and dust like the Orion Nebula, where gravity is patiently sculpting new suns and planetary systems into existence. We can observe the death throes of ancient stars, which explode in brilliant supernovae that seed space with the heavy elements, the carbon, oxygen, and iron that are essential for building planets and, ultimately, life. Every image we take of our own galaxy is therefore an impossible collage, a photograph that captures tens of thousands of years of history all at once. We are never seeing a single moment, but a time-lapse view of a structure that is constantly in motion. And it is indeed in motion. The entire galaxy spins like a colossal, glittering pinwheel. Our solar system is carried along on this cosmic carousel, completing one full orbit of the galactic center approximately every 230 million years. This is sometimes called a galactic year. The last time our solar system was in this same position in its orbit, the very first dinosaurs were just beginning to evolve and walk the Earth. The time before that, the planet was still recovering from the Permian-Triassic extinction, the most devastating mass extinction event in its history, which wiped out over 90% of all species. This constant rotation means that the galaxy literally changes its shape during the time it takes for light to cross it. The stars on the far side that emitted the light we see tonight are no longer in that position. They have moved halfway around the galaxy since that ancient light began its journey. Our galaxy, with its hundreds of billions of stars, its mind-crushing scale, and its deep-time phenomena, feels like the very definition of immensity. To stand on the surface of our small planet and contemplate this structure is an act of profound intellectual expansion. The ancient Greeks imagined the stars were mere holes punched in a celestial sphere that enclosed the Earth. Today we know that our cosmic home is a dynamic, evolving ecosystem of stars and gas that would have shattered their every conception of reality. It contains enough potential worlds to fuel 1,000 mythologies and enough cosmic power to dwarf any force we have ever experienced. But here is the most unsettling realization of all. This entire galactic structure, this city of 400 billion suns that takes light 100 millennia to cross, is just the beginning. It is the first, smallest, most intimate step on a cosmic ladder that climbs to scales of organization so vast they make our entire galaxy seem like a single, insignificant speck of dust. This cosmic city of 400 billion suns, a structure so vast it seems to defy comprehension, presents us with a profound paradox. When we look up on a clear, dark night, far from the glare of city lights, the sky appears densely packed with stars. The Milky Way's luminous band looks like a thick, glowing river of light. A celestial cloud so crowded that it seems impossible to find an empty patch within it. This appearance, however, is one of the grandest illusions in the cosmos. In reality, our galaxy is defined not by its substance, but by its staggering, almost absolute emptiness. The space between the stars is so immense that it renders the stars themselves into little more than mathematical points in an ocean of void. Let's begin with our immediate neighborhood. The Sun's closest stellar companion is a small, dim, red dwarf star named Proxima Centauri. It is part of the 3-star Alpha Centauri system and is our very next-door neighbor on the cosmic street. How far away is next door? It is 4.24 light-years from us. This distance, just over 4 years at the universe's ultimate speed limit, translates to about 25 trillion miles. A number that large is functionally meaningless to the human brain. To give it context, if you were to board the Parker Solar Probe, the fastest object humanity has ever built, and point it directly at Proxima Centauri, your journey would last approximately 19,000 years. You would need to travel through time from the era when humans were first domesticating dogs to the present day, just to complete one leg of that trip. Let's scale it down again to try and grasp this void. Imagine the sun is shrunk to the size of a standard grapefruit, about 5 inches in diameter. At this scale, the Earth would be a single grain of salt orbiting about 45 feet away. Jupiter would be a small marble over 200 feet away. The entire solar system, out to Neptune, would fit comfortably within a couple of city blocks. Where then is our nearest neighbor, the next grapefruit representing Proxima Centauri. It would be in another city. If our grapefruit sun is in Los Angeles, the neighboring one would be in Phoenix, Arizona, some 350 miles away. And between those two grapefruits, across hundreds of miles of scaled-down space, there would be essentially nothing, just a few scattered molecules of gas and microscopic dust particles, adrift in a near-perfect vacuum. This is the fundamental nature of our galaxy. It is a structure composed almost entirely of this mind-numbing emptiness. The average distance between stars in our region of the galaxy is about 5 light-years. This stellar isolation has profound consequences. It means that, for all practical purposes, every star system is an island universe, marooned in a sea of nothingness. The dream of casual interstellar travel, of hopping from one star system to another, as we might hop between islands in an archipelago, crashes against the unforgiving reality of this void. The energy requirements to cross these gulfs are astronomical, and the time required is geological. This emptiness is also the most compelling, if unsettling, answer to the famous question, where is everybody? Known as the Fermi paradox, it highlights the contradiction between the high probability of extraterrestrial life existing among billions of Earth-like planets in our galaxy, and the complete lack of any evidence for it. The great void between the stars provides a powerful explanation. Our galaxy could be teeming with thousands of intelligent civilizations, but each one would be trapped on its own isolated island. The distances are simply too great for meaningful communication or interaction. If a civilization on the opposite side of the galaxy, 100,000 light-years away, were to send us a message traveling at the speed of light, it would not arrive for 100,000 years. Human civilization has only existed in any recognizable form for a tiny fraction of that time. The conversation would be impossible. The sender might be long extinct by the time their hello even reached us. The universe, through its sheer scale, enforces a cosmic quarantine. The space between the stars is not a true perfect vacuum, but it is closer to one than anything we can create in a laboratory on Earth. This interstellar medium consists of an incredibly tenuous soup of individual atoms, mostly hydrogen and the helium, with a smattering of dust grains. The density is, on average, about 1 atom per cubic centimeter. For comparison, the air you are breathing right now contains about 30 quintillion atoms in that same volume. To swim through interstellar space would be to encounter individual atoms separated by yards of emptiness. It is this medium that, over millions of years, can be slowly herded together by gravity to form the dense nebulae from which new stars are born. But on human timescales, it is a void of unimaginable purity. This fundamental emptiness also ensures that the cosmos is far less violent on a stellar level than you might imagine. We know that our galaxy is on a collision course with our larger neighbor, the Andromeda Galaxy. In about 4.5 billion years, these two colossal structures will merge. Yet, even during this cataclysmic galaxy-scale event, the number of direct star-on-star collisions will be virtually zero. The individual stars are simply too small, and the space between them too vast. It would be like two swarms of bees, each occupying a volume the size of a continent, flying through each other. The odds of any two bees actually hitting each other would be infinitesimally small. The galaxies will pass through each other like ghosts, their shapes distorted and reorganized by gravity, but their individual stars will sail past one another, untouched by anything but the pull of their combined mass. So, when you gaze upon the Milky Way, remember the illusion. You are not seeing a crowded thoroughfare. You are seeing a realm of profound cosmic loneliness. Every single star you see is an isolated campfire in an impossibly vast and dark wilderness. Our planet, our sun, our entire solar system is just one such campfire, and the distance to the next flicker of light is a chasm that our species may never be able to cross. We inhabit a tiny oasis of matter in an overwhelming desert of the void, and yet, this desert, this empty space that defines our entire galaxy, is itself just our immediate backyard. As we prepare to take the next step up the cosmic ladder, we will discover that this galactic emptiness looks positively crowded, compared to the gulfs that separate the galaxies themselves. Our journey into cosmic scale has so far been confined to our home galaxy, a structure so vast it seems a universe unto itself. Yet, the Milky Way, with its immense voids and isolated stars, does not drift through the cosmos alone. It is a member of a family, a gravitationally bound collection of galaxies known as the local group. This is the next rung on the cosmic ladder, a structure that introduces a new level of organization and complexity. To comprehend the local group is to realize that our entire galaxy, the container of 400 billion suns, is just one of two dominant siblings in a sprawling cosmic clan. This galactic neighborhood spans a staggering 10 million light-years, a volume of space so large that our own galaxy is just a single point of light within it. The undisputed heavyweight champion of the local group is not us. It is the Andromeda Galaxy, also known as M31, visible to the naked eye as a faint, fuzzy smudge in the autumn sky. Andromeda is a cosmic titan. It is larger, brighter, and more massive than the Milky Way, stretching over 220,000 light-years from edge to edge and containing perhaps 1 trillion stars. If our galaxy is a sprawling metropolis like New York City, Andromeda is an entire continent-spanning empire. The light you see from it tonight is a ghost from the deep past. It began its journey across the intergalactic void 2.5 million years ago. When those photons left Andromeda, our distant ancestors, early hominins like Australopithecus, were roaming the savannas of Africa. The galaxy we observe is not the galaxy that exists today. It is a snapshot of how it looked long before modern humans ever walked the Earth. Andromeda and the Milky Way are the two gravitational anchors of the local group. Together, they dominate the region, their immense gravitational pull orchestrating the movements of all the other members, and they are moving towards each other. Precise measurements of Andromeda's motion have confirmed a startling fact. It is hurtling in our direction at a speed of about 250,000 miles per hour. This is not a near miss. It is a head-on collision course. In approximately 4.5 billion years, our two galaxies will begin a spectacular and protracted process of merging. Over hundreds of millions of years, they will pass through each other, their spiral arms torn apart by tidal forces, flinging vast streams of stars and gas into intergalactic space. After several chaotic passes, they will finally settle down, their combined mass coalescing into a single, giant elliptical galaxy, which some astronomers have already nicknamed Milkomeda. As terrifying as this galactic merger sounds, our solar system will likely emerge unscathed. As we discovered, the space between stars is so vast that direct collisions are almost non-existent. Instead, the Sun and its planets will simply be cast into a new, looping orbit around the newly formed galactic core. Future inhabitants of Earth would be treated to a night sky of unimaginable splendor, filled with brilliant bursts of star formation, as the combined gas clouds of the two galaxies are compressed, igniting billions of new suns. Beyond these two giants, the local group contains over 50 other, smaller galaxies. Most of these are dwarf galaxies, cosmic minnows containing just a few billion, or even only millions, of stars. They are like small towns and villages orbiting the two major metropolitan centers of Andromeda and the Milky Way. The most famous of these are the Large and Small Magellanic Clouds, visible as irregular patches of light from the southern hemisphere. These are not just passive companions. They are in a constant violent relationship with our own galaxy. The Milky Way's immense gravity is actively tearing them apart, siphoning off streams of gas and stars in a process of galactic cannibalism. This stellar material is being incorporated into our own galaxy, feeding its growth over billions of years. This process is a fundamental aspect of cosmic evolution. Large galaxies like ours were not born in their current state. They grew to their immense size by consuming their smaller neighbors over eons. The entire local group, this collection of more than 50 galaxies, moves through the universe as a single, coherent unit. It is not stationary. Our whole cosmic family is currently traveling at over 1.3 million miles per hour relative to the cosmic microwave background radiation. the faint afterglow of the Big Bang. This motion is not random. We are being pulled. We are passengers on a cosmic river, flowing towards an unseen, massive gravitational anomaly that lies far beyond the boundaries of our local neighborhood. What holds this entire structure together? The visible matter, the stars, gas, and dust, is not nearly enough. If you were to add up the mass of all the trillions of stars in the local group, their combined gravity would be far too weak to bind the galaxies in their observed orbits. They should have all flown apart billions of years ago. The solution to this puzzle is a substance that we cannot see, touch, or detect in any direct way: dark matter. Scientists have confirmed that our local group, like all galactic structures, is embedded within a massive, invisible halo of this mysterious substance. This dark matter halo contains roughly 10 times more mass than all the visible matter combined. It is the invisible gravitational scaffolding, the cosmic glue that holds our galactic family together, allowing it to resist the overall expansion of the universe. So, our perception must shift again. Our galaxy is not an island, but part of an archipelago. This archipelago is not static, but a dynamic, evolving system of mergers, cannibalism, and graceful orbital dances that unfold over billions of years. And this entire system, bound by an invisible substance, is itself a vessel, sailing through the vaster ocean of intergalactic space. The local group, spanning 10 million light-years, is our greater home, our cosmic county. But as we will soon see, this county is just a tiny district within an even larger cosmic metropolis. Having journeyed from the vast emptiness between stars to the gravitationally bound family of our local group, we now take another monumental leap in scale. Our local group, with its 10 million light-year span and its collection of over 50 galaxies, is but a small suburban outlier on the edge of a much grander structure, a galaxy cluster. These are the true cosmic cities of the universe, gravitationally bound systems containing not dozens, but hundreds or even thousands of individual galaxies. They are the most massive, stable structures known to exist. Immense concentrations of matter and energy that bend space-time itself across millions of light-years. Our nearest major urban center in this cosmic hierarchy is the Virgo cluster. Located approximately 54 million light-years away, the Virgo cluster is a sprawling metropolis of galaxies. To grasp this distance, remember that the light from our nearest major galactic neighbor, Andromeda, takes 2.5 million years to reach us. The light from the heart of the Virgo cluster began its journey more than 20 times earlier. It left its source when the first apes were just beginning to evolve on Earth, long before the emergence of the human lineage. When we observe the Virgo cluster, we are peering into a past so deep that it predates our own species by an almost unimaginable margin. The Virgo cluster contains at least 1,300, and perhaps as many as 2,000, individual galaxies packed into a volume of space roughly 15 million light-years in diameter. Unlike our local group, which is dominated by two large spiral galaxies, the Virgo cluster is a much more diverse and chaotic environment. At its heart lie three colossal elliptical galaxies: Messier 87, Messier 86, and Messier 84. These are galactic behemoths, each containing trillions of stars and dwarfing both the Milky Way and Andromeda. Messier 87, in particular, is a cosmic monster. It is home to several trillion stars and one of the most massive black holes ever discovered, a supermassive black hole with a mass 6.5 billion times that of our Sun. This is the very same black hole that was the subject of the first ever direct image captured by the Event Horizon Telescope, a feat of global scientific collaboration. The environment within a galaxy cluster is fundamentally different from the relative tranquility of our local group. The galaxies in the Virgo cluster are packed together much more densely, and they are moving at incredible speeds. Individual galaxies whip through the cluster at velocities approaching 3.5 million miles per hour. At these speeds, galactic interactions are frequent and violent. Galaxies constantly sideswipe each other, their gravitational forces stripping away gas and distorting their shapes. This process, known as ram pressure stripping, is like a cosmic wind that scours gas out of a galaxy as it plunges through the hot, dense medium that fills the cluster. This is why the dominant galaxies in the cores of clusters are often giant ellipticals. They are the end product of numerous galactic mergers and have had their star-forming gas stripped away, leaving them as massive, quiescent collections of old red stars. But this raises another profound mystery. Just like with the local group, the visible matter in the Virgo cluster is not nearly enough to hold it together. The galaxies are moving so fast that the cluster should have flown apart, dissipating into the cosmic void billions of years ago. The gravitational pull of all the stars and gas we can see is woefully insufficient to counteract this kinetic energy. The solution, once again, is dark matter. Galaxy clusters are the ultimate proof of dark matter's existence. In the Virgo cluster, dark matter outweighs all the visible matter, all the trillions upon trillions of stars, by a factor of at least 10 to 1. It forms an immense cosmic basin that traps the thousands of galaxies within its grasp. We can't see this dark matter, but we can map its presence through a phenomenon called gravitational lensing. The immense mass of the cluster, primarily its dark matter component, warps the fabric of space-time so severely that it acts like a giant magnifying glass. Light from more distant galaxies, located far behind the cluster, is bent and distorted as it passes through this gravitational field. By analyzing the precise patterns of this distortion, astronomers can create a map of the invisible mass, revealing the vast dark matter scaffold that underpins the entire structure. Furthermore, the space between the galaxies in the Virgo cluster is not empty. It is filled with a superheated, incredibly tenuous gas called the intracluster medium. This plasma, heated to temperatures of over 100 million degrees Celsius, is hotter than the core of the sun. It is so hot that it glows brightly in X-ray light, making galaxy clusters some of the most luminous X-ray sources in the sky. Incredibly, this invisible superheated gas contains more ordinary baryonic matter than all of the stars in all of the cluster's 1,000+ galaxies combined. So, the vast majority of the normal matter in a cluster isn't in the galaxies at all, but is spread out between them. The Virgo cluster is not a passive bystander in our cosmic story. It is the dominant gravitational force in our corner of the universe. Our own local group, including the Milky Way and Andromeda, is currently being pulled towards the Virgo cluster. We are, in a sense, falling into this great cosmic city. We are part of what is known as the Virgo supercluster, a vast collection of galaxy groups and clusters of which Virgo is the gravitational heart. This journey towards Virgo is a slow-motion infall that has been happening for billions of years, a testament to the irresistible pull that these massive cosmic structures exert across hundreds of millions of light years. Our cosmic journey has expanded exponentially from our galactic home across our local family and into the gravitational basin of the Virgo cluster. Each step has revealed a new, grander level of organization, making the previous one seem almost provincial by comparison. But even a structure as immense as the Virgo cluster, a cosmic city of thousands of galaxies, is not the final word on cosmic architecture. It is merely a single, prominent landmark within a structure so vast, so sprawling, that it fundamentally redefined our understanding of our place in the universe. This structure is our home supercluster, a colossal filament of galaxies known as Laniakea. It spans an incredible 520 million light years. To traverse this structure, even at the speed of light, would take more than 500 million years. When the light from the far side of Laniakea began its journey towards us, the first complex multicellular life was just beginning to appear in the oceans of Earth. The continents were arranged in a configuration we would barely recognize. This is the scale of our greater cosmic home. It is a structure that binds together tens of thousands of galaxy clusters and groups, containing a total mass of about 100 quadrillion times that of our Sun. The Virgo cluster, which once seemed like the dominant center of our cosmic world, is revealed to be just a provincial hub within this supercluster. It is a major component, but it is not the ultimate destination of the cosmic flow. The name Laniakea is Hawaiian for immeasurable heaven, and it is a name well earned. Discovered in 2014, Laniakea is not just a collection of galaxies, but a coherent gravitational domain. It is defined not by where galaxies are, but by where they are going. A team of astronomers mapped the peculiar velocities of tens of thousands of galaxies in our cosmic neighborhood. Peculiar velocity is the motion of a galaxy separate from the overall expansion of the universe. In other words, they were mapping the gravitational flows of the local cosmos, like cartographers charting the water currents in an ocean. What they found was astonishing. Our local group, the Virgo cluster, and about 100,000 other galaxies are all part of a single, massive gravitational basin. They are all flowing inwards, like rivers draining into a single valley, towards a common center of gravity. This entire watershed, this continental-scale structure of galaxies is Laniakea, the true gravitational heart of Laniakea. The point where all the galactic streams are converging is a region of immense density known as the Great Attractor. This is a cosmic anomaly that astronomers have been aware of for decades, a mysterious concentration of mass that has been pulling our galaxy and countless others towards it. For years, its exact nature was obscured from our view, hidden behind the dense gas and dust of our own Milky Way's disk. With the mapping of Laniakea, we now understand that the Great Attractor is a focal point within a much larger structure. It is a massive node where several galactic filaments converge, creating an exceptionally deep gravitational well. Our own galaxy, the Milky Way, is being pulled towards this point at a speed of over 1.4 million miles per hour. We are on a multi-billion-year trajectory, a slow-motion infall towards the heart of our home supercluster. However, the concept of a supercluster like Laniakea is more fluid and ephemeral than that of a galaxy cluster. While a cluster like Virgo is gravitationally bound, meaning its internal gravity has overcome the expansion of the universe and will hold it together forever, a supercluster is different. Laniakea is so vast that the accelerating expansion of the universe, driven by dark energy, is fighting against its internal gravity. On the outer edges of Laniakea, the cosmic expansion is winning. Galaxies on the periphery are not just flowing inwards. They are also being carried away as the fabric of space-time itself stretches. Laniakea, therefore, is not a permanent, bound object. It is a temporary gathering, a magnificent but transient pattern in the cosmic flow that will eventually be pulled apart by dark energy over the course of future eons. Visualizing Laniakea is to picture a structure that looks more biological than astronomical. It is not a sphere or a simple clump. It is a vast, tendrilled, filamentary network. Imagine a three-dimensional map of interconnected highways and byways, with galaxies and galaxy clusters acting as the cities and towns along these routes. Our local group is on one of these filaments, a cosmic backroad leading towards the more densely populated regions of the Virgo cluster, which in turn lies on a larger superhighway heading towards the Great Attractor. The discovery of Laniakea represented a paradigm shift. For the first time, we had a clear definition of our cosmic address on the supercluster scale. It is like discovering not only your city and state, but the continent on which you reside. Our planet, Earth, is in the solar system, which is in the Orion spur of the Milky Way galaxy. The Milky Way is a member of the local group, which is an outlying component of the Virgo supercluster complex. And this entire structure is just one filament within the immeasurable heaven of the Laniakea supercluster. This magnificent, sprawling structure of 100,000 galaxies, bound in a delicate and temporary dance between gravity and cosmic expansion, is our true home on the largest of scales. But even this continent of galaxies is just one piece of an even grander global architecture. Having defined our home continent of Laniakea, a structure of 100,000 galaxies held in a delicate gravitational dance, we must now zoom out one final time to behold the ultimate scale of cosmic organization. If superclusters are the continents of the universe, then what does the globe look like? Matter in the universe is not scattered randomly like sand thrown into the wind. Instead, it is organized into a vast, interconnected, three-dimensional network that permeates all of space. This is the grandest structure known to exist, the cosmic web. The cosmic web is the architectural blueprint of the universe. It resembles a colossal, shimmering spider web or the intricate neural network of a brain, stretching across billions of light years. Computer simulations of the early universe, combined with massive observational surveys that have mapped the positions of millions of galaxies, confirm that this structure is the natural and inevitable result of gravity acting on tiny quantum fluctuations present just after the Big Bang. Over 13.8 billion years, gravity has patiently woven the matter of the cosmos into this magnificent and intricate tapestry. The web has several distinct components. The densest parts are the nodes or clusters, which we have already visited. These are the bright, busy intersections where multiple filaments meet, forming massive galaxy clusters like Virgo. They are the great cosmic cities, containing thousands of galaxies in a relatively small volume. Stretching between these nodes are the filaments. These are the highways of the cosmic web, enormous thread-like structures of galaxies, gas, and dark matter that can span hundreds of millions of light years. Laniakea itself is essentially one such filament. These cosmic bridges channel matter from less dense regions into the clusters, acting as a cosmic plumbing system that feeds the growth of the universe's most massive structures. Where these filaments intersect in broad, they form walls. These are vast, sheet-like structures of galaxies that can stretch for over 1 billion light years, representing some of the largest single coherent objects ever discovered. One of the most famous is the Sloan Great Wall, a chain of superclusters and galaxies that extends for 1.4 billion light years. If you were to travel its length at the speed of light, your journey would take longer than the entire time that complex life has existed on Earth. And then, between all of this structure, the clusters, the filaments, and the walls, lie the voids. These are the great, dark, empty spaces of the cosmos. They are immense, nearly spherical bubbles of near nothingness, often hundreds of millions of light years in diameter. They are the parts of the universe from which matter has drained away, flowing down the gravitational gradients to form the web's luminous structures. These voids dominate the volume of the universe, meaning that most of the cosmos is, in fact, empty space. The galaxies, in all their glory, are merely the luminous froth on the edges of these colossal cosmic bubbles. The engine behind this entire architecture is, once again, dark matter. In the early universe, dark matter, being immune to the pressure of light and radiation, began to clump together under its own gravity much earlier than normal matter. It formed an invisible cosmic scaffolding, a gravitational blueprint in the shape of a web. Normal matter, the hydrogen and helium gas that would eventually form stars and galaxies, was then drawn into this pre-existing dark matter framework, lighting up the filaments and nodes like streetlights along a pre-built road network. We see the galaxies because they shine, but they are tracing an underlying structure of darkness that is 5 times more massive and vastly more extensive. The cosmic web is not a static museum piece. It is a dynamic, evolving ecosystem. Matter continues to flow along the filaments, draining from the voids and accreting onto the clusters. The clusters themselves, located at the web's major intersections, are still growing, continuing to merge with other groups and clusters that are funneled towards them. At the same time, the entire web is being stretched and pulled apart by the accelerating expansion of the universe. Over cosmic timescales, the filaments will become more tenuous, and the clusters will become more isolated, as dark energy pushes the great structures ever farther apart. This vision of the universe as a web fundamentally changes our perspective. Our Milky Way is not an isolated entity, but a single point of light in a single filament. Our entire supercluster Laniakea is just one thread in an incomprehensibly vast tapestry. All of cosmic history, from the formation of the first stars to the evolution of life on Earth, has played out within this grand, interconnected structure. It is a structure of stunning beauty and elegance, revealing a universe that is not chaotic, but profoundly and deeply organized on the largest possible scales. It is the final, breathtaking vista that emerges when we zoom all the way out, revealing the true architecture of existence. We have marveled at the luminous architecture of the cosmic web, the intricate network of filaments, walls, and clusters that house the universe's 2 trillion galaxies. It is a structure of immense beauty and complexity. Yet, to focus solely on these bright threads is to miss the biggest part of the picture. The defining feature of the cosmic landscape, in terms of sheer volume, is not the substance, but the absence. The vast majority of the universe is composed of the great cosmic voids. These are the colossal, underdense bubbles that the cosmic web envelops, regions of space so empty they challenge our very definition of nothingness. To journey into a void is to journey into the great cosmic desolation. Cosmic voids are the largest and most sparsely populated environments in the universe. They are immense, roughly spherical regions that have been emptied of matter by the gravitational pull of the surrounding cosmic web. As gravity herded galaxies into the filaments and clusters, it left these vast domains behind. A typical void can span anywhere from 30 million to 300 million light-years in diameter, but some are far larger. For perspective, our entire local group of galaxies could be tucked into a tiny corner of an average-sized void, and we would be utterly lost within it. The most famous of these is the Boötes Void, sometimes called the Great Nothing. Discovered in 1981, it is a staggering 330 million light-years across. If we were to place our Milky Way galaxy at the center of the Boötes Void, the night sky would be an almost perfect, terrifying blackness. From Earth, we can see thousands of individual stars with the naked eye and countless galaxies with a simple telescope. From a planet inside the void, you would see almost nothing. The nearest major galaxy would be so distant that its existence would not have been confirmed by our astronomers until the 1960s, with the advent of powerful radio telescopes. The discovery that we lived in a galaxy, let alone that other galaxies existed, would have been a profoundly more difficult and delayed realization for any civilization unlucky enough to be born there. Despite their name, voids are not completely empty. They do contain some matter, but at a density less than 1/10 of the cosmic average. They are home to a few scattered void galaxies. These rare and lonely galaxies are fascinating objects of study. Because they have evolved in extreme isolation, they are pristine examples of galaxy formation, untouched by the mergers and gravitational harassment common in denser environments. They tend to be smaller, bluer, and more actively forming stars than their counterparts in the cosmic web, like wildflowers blooming in a vast, empty desert. The voids also contain a tenuous web of dark matter filaments, a sort of web within the web, but this scaffolding is too weak to have captured significant amounts of normal matter. The emptiness of the voids is profound. The temperature inside a void hovers just a few degrees above absolute zero, the coldest possible state of matter. The density of particles is so low that individual atoms might be separated by yards or even miles of empty space. This is a vacuum far more perfect than anything humanity can create in a laboratory. It is a realm of extreme silence and stillness, where cosmic evolution has effectively ground to a halt. These voids are not just passive byproducts of cosmic structure formation, they actively shape the universe we see. Because they contain so little matter, they have a weaker gravitational pull. This means they act as a kind of cosmic anti-gravity. As photons from the cosmic microwave background, the afterglow of the Big Bang, travel through a void, they lose a tiny bit of energy. This is because they have to climb out of the gravitational well of the filament on one side, but there is less matter on the other side to give them a gravitational kick as they exit. This effect creates subtle cold spots in our maps of the ancient universe, providing another way for astronomers to map the locations and sizes of these great empty regions. Furthermore, the voids are where the expansion of the universe is most apparent and dominant. Inside a dense cluster, gravity has won the battle against cosmic expansion, but inside a void, There is almost no gravity to resist the stretching of space-time. Here, dark energy reigns supreme. The voids are getting larger over time, pushing the filaments and walls of the cosmic web further apart. They are the engines driving the accelerating isolation of the universe's great structures. In total, these cosmic voids are estimated to occupy roughly 80% of the volume of the observable universe. This is a staggering realization. The universe we know, the galaxies, the stars, the planets, the very stuff of our existence, is confined to the thin, luminous membranes of the cosmic web, which themselves constitute only about 20% of cosmic space. We live in the cosmic equivalent of a handful of islands scattered across an ocean that covers 80% of the globe. The story of the universe is not just the story of how matter came together, but also the story of how these immense regions of nothingness were formed, and how they continue to shape the ultimate fate of the cosmos. Our journey has taken us through an astonishing hierarchy of structures, from the lonely voids between stars to the vast interconnected cosmic web. We have traveled across billions of light years in our imagination, witnessing the grand architecture of reality on its largest scales. But now we must confront a fundamental limit, a boundary not made of matter or energy, but of time and light itself. This is the edge of the observable universe, a conceptual horizon that defines the absolute limit of everything we can ever hope to see or interact with. It is not a physical wall at the end of space, but rather a temporal one, a barrier erected by the finite age of the cosmos and the ultimate speed limit of light. The universe, as best we can tell, began 13.8 billion years ago with the Big Bang. Since that moment, light from the most distant objects has been traveling through space to reach us. The observable universe is simply the spherical region of space containing all the matter from which light has had enough time to arrive at Earth in those 13.8 billion years. Anything beyond this sphere is, for now, completely invisible to us. Not because space ends there, but because its light has not yet completed the marathon journey to our telescopes. This concept leads to one of the most counterintuitive facts in cosmology. One might naively assume that if the universe is 13.8 billion years old, the edge of what we can see must be 13.8 billion light years away. But this assumption is wrong. It fails to account for a crucial factor: the expansion of space. In the time it took for light from a distant object to travel towards us, the space between us and that object has been continuously stretching. The object that emitted the light 13.8 billion years ago is no longer 13.8 billion light years away. It has been carried much, much farther by the relentless expansion of the universe. Current calculations place the actual edge of the observable universe at approximately 46.5 billion light years in every direction, giving it a total diameter of 93 billion light years. So, when we look at the most distant galaxy we can detect, we are seeing its light as it was emitted perhaps 13.2 billion years ago, when the universe was just a toddler. But that galaxy today, in its present form, is now over 30 billion light years away from us, far beyond the point where its light was originally emitted. We are seeing its baby picture, while its adult self has receded to an unobservable distance. This horizon has a deeply personal and relative nature. Every observer in the universe, on any planet in any galaxy, is at the center of their own unique observable universe. An astronomer in a galaxy 10 billion light years from us would see a sphere of space 93 billion light years in diameter centered on them. Their observable universe would overlap with ours in some regions, but they would also be able to see vast swaths of the cosmos that are forever hidden from our view, and vice versa. There is no single objective center of the universe. Every point is the center of its own observational bubble. The absolute edge of our vision is marked by a faint, pervasive glow that fills the entire sky, detectable in microwave frequencies. This is the cosmic microwave background, CMB. It is the oldest light in the universe, a fossilized afterglow from the Big Bang itself. It was emitted about 380,000 years after the Big Bang, at a moment called recombination. Before this time, the universe was a hot, dense, opaque plasma, like the interior of a star. Light couldn't travel freely. It was constantly scattered by charged particles. When the universe expanded and cooled enough for protons and electrons to combine into the first stable atoms, space suddenly became transparent. The light that was present at that moment was finally set free, and it has been traveling across the cosmos ever since. The CMB is that very light, stretched by cosmic expansion from a brilliant white-hot glow into the cool, invisible microwaves we detect today. This wall of ancient light represents the furthest back in time we can ever see with any kind of telescope. It is the boundary between a transparent universe and an opaque one. Peering beyond the CMB is like trying to see the center of the sun. It's impossible. Anything that happened in the first 380,000 years of cosmic history is hidden behind this primordial curtain of light. And this boundary is not static. Our observable universe is constantly growing. Every second, 1 light second of new cosmic territory becomes visible in every direction as light that has been traveling for 13.8 billion years finally arrives. However, this growth is in a race against the accelerating expansion of the universe. In the far future, dark energy will cause distant galaxies to recede from us faster than the speed of light. They will cross over a cosmic event horizon, their light no longer able to reach us. As time goes on, more and more galaxies will disappear from our view. The observable universe, in terms of the number of galaxies it contains, will begin to shrink. We are living in a privileged epoch, a golden age of cosmology where we can see a vast and rich cosmic history that will be hidden from astronomers in the distant future. The edge of our universe is both a window into the deep past and a stark reminder of our fundamental cosmic limitations. Having established the immense 93 billion light-year boundary of our observable universe, a natural and staggering question arises. What's inside? How much stuff is contained within this cosmic sphere? To answer this, astronomers have undertaken the most ambitious census in history, pointing our most powerful telescopes at tiny, seemingly empty patches of sky and staring, motionless, for days and weeks on end. The results of these deep field observations have fundamentally shattered our perception of cosmic population density and our own place within it. The most famous of these experiments is the Hubble Ultra Deep Field. Astronomers chose a minuscule spot in the constellation Fornax, a region of the sky so empty it was devoid of any bright stars. It was a patch of darkness equivalent in size to a grain of sand held at arm's length. Over the course of 11 days, the Hubble Space Telescope opened its eye and collected every single photon that trickled in from this dark window. When the final image was assembled, it was not black. It was a breathtaking jewel-studded tapestry containing nearly 10,000 points of light. And every single one of those points, with the exception of a handful of foreground stars, was not a star, but an entire galaxy. Some were majestic spirals like our own. Others were fuzzy red ellipticals, and many were small, irregular blue smudges, the infant galaxies of the early universe. This single image, covering a trivial 13 millionth of the total sky, became a cosmic core sample. By extrapolating the number of galaxies found in this tiny patch to the entire celestial sphere, astronomers could make a robust estimate of the total number of galaxies within our observable horizon. For many years, the working number was around 100 to 200 billion galaxies. But as telescope technology improved and our models of the early universe grew more sophisticated, this number was revised dramatically upwards. The current, most widely accepted estimate, based on data from Hubble and other observatories, is that our observable universe contains approximately 2 trillion galaxies. Let this number sink in. Not 200 billion, but 2 trillion. That is a 2 followed by 12 zeros. It is a number so large that our minds simply cannot process it in any intuitive way. If you were to count these galaxies at a rate of 1 per second, it would take you nearly 63,400 years to finish. You would have to start your count during the last ice age and continue without pause to the present day. Now, let's consider what each of these galaxies contains. Our own Milky Way is a fairly average-sized spiral galaxy, and it contains somewhere between 100 and 400 billion stars. Using a conservative average of 100 billion stars per galaxy, we can multiply these two colossal numbers together. The result is an estimate for the total number of stars in the observable universe, 200 sextillion. That is a 2, followed by 23 zeros. This number is famously compared to the number of grains of sand on all the beaches and deserts of Earth. The latest estimates put the sand grain count at around 7 quintillion. This means that for every single grain of sand on our entire planet, there are more than 20,000 stars shining out there in the cosmos. This cosmic census has profound, almost philosophical implications. It forces a radical recalibration of our own significance. Our entire galaxy, the Milky Way, with its 400 billion suns and 100,000 light-year span, is just one of 2 trillion. Our sun is just one of 200 sextillion. If we consider the number of planets, the figures become even more ludicrous. Current exoplanet research suggests that, on average, every star in the galaxy hosts at least one planet. This means there are likely more planets in the universe than there are stars. Trillions upon trillions of worlds. Billions of these are likely to be rocky planets orbiting in the habitable zone of their stars, where liquid water could potentially exist. Even if life is an astonishingly rare phenomenon, the sheer statistical weight of these numbers is overwhelming. If just 1 in a billion stars hosts a planet with life, there would still be hundreds of millions of living worlds in our galaxy alone. If intelligent life is a 1 in a trillion shot, the universe could still be home to millions of civilizations. The universe is not just big, it is populous beyond our wildest imaginings. These deep field images are also time machines. Because the light from these galaxies has traveled for billions of years, we are seeing them as they were in the distant past. The faintest, reddest smudges in the Hubble ultra-deep field are galaxies that existed when the universe was less than 1 billion years old. We are seeing the first generations of galaxies as they were just beginning to form, providing invaluable snapshots of cosmic evolution in action. The 2 trillion galaxy count may even be an underestimate. Many of the universe's galaxies are small, faint dwarf galaxies that are incredibly difficult to detect, even for Hubble. As the next generation of telescopes, like the James Webb Space Telescope, peers even deeper into the infrared spectrum, it is likely that we will uncover vast populations of these dimmer galaxies, potentially pushing the final count even higher. This staggering inventory of worlds forces us to see our own existence in a new light. We are a single data point in a census of 2 trillion, a tiny, fleeting thought in an unimaginably vast cosmic mind. We have now painted a picture of the universe staggering in its scale and population, a cosmic web containing 2 trillion galaxies, stretching across 93 billion light-years. And yet, this entire luminous structure, all the stars, planets, gas, and dust we can see, accounts for a shockingly small fraction of what is actually out there. The vast majority of the universe is composed of 2 invisible components that govern its evolution and will ultimately decide its fate. The first is dark matter, the invisible scaffolding that holds galaxies together. The second, and by far the most dominant and mysterious, is dark energy. This is not a substance in the conventional sense. It is a pervasive, repulsive force woven into the very fabric of space-time itself, and it is tearing the universe apart. For most of the 20th century, cosmologists debated 2 possible futures for the universe. In one scenario, the Big Crunch, the mutual gravitational attraction of all the matter in the cosmos would eventually overcome the initial outward momentum of the Big Bang, causing the expansion to slow down, stop, and reverse, culminating in a cataclysmic collapse. In the other, the Big Freeze, gravity would not be strong enough, and the universe would expand forever, growing colder, darker, and emptier as its stars burned out. The deciding factor was the total density of matter and energy in the universe. Then, in 1998, 2 independent teams of astronomers made a discovery that completely upended cosmology and earned them the Nobel Prize. They were using distant type Oa supernovae, a type of exploding star with a known standardized brightness, as standard candles to measure the expansion rate of the universe at different points in its history. They expected to find that the expansion was slowing down due to gravity. Instead, they found the exact opposite. The expansion of the universe is accelerating. Something is actively pushing space apart, and this repulsive force is growing stronger over time. This something was given the placeholder name, dark energy. According to our best current measurements, dark energy makes up about 68% of the total energy density of the universe. Dark matter accounts for another 27%. This leaves the normal baryonic matter, everything we have ever seen or touched, every star, galaxy, and planet, as a mere 5% of the cosmic total. We are, in a very real sense, living in a universe dominated by forces we do not understand and substances we cannot see. The nature of dark energy is the single greatest mystery in modern physics. The leading hypothesis is that it is a form of vacuum energy, an intrinsic property of empty space itself. According to quantum mechanics, empty space is not truly empty, but is fizzing with virtual particles that pop in and out of existence. This quantum foam could, in theory, exert a negative pressure, pushing space apart. The problem is that when physicists try to calculate how strong this vacuum energy should be based on quantum theory, they get a number that is 120 orders of magnitude larger than what we observe. This discrepancy, known as the cosmological constant problem, is the most spectacular failure of a prediction in the history of science. Regardless of its origin, the effects of dark energy are profound and inescapable. It acts as a cosmic anti-gravity. On smaller scales, like within our solar system, or even our local group of galaxies, the gravitational pull of matter is strong enough to overcome dark energy's gentle push. But on the vast scales between superclusters, dark energy is the dominant force, and its influence is growing. As space expands, the density of matter and dark matter decreases as it's spread out over a larger volume. But the density of dark energy, being an intrinsic property of space itself, appears to remain constant. Every new cubic meter of space that is created comes with its own allotment of dark energy. This means that as time goes on, dark energy's repulsive force becomes increasingly dominant over gravity's attraction. This accelerating expansion dictates the ultimate fate of our universe. The Big Crunch is off the table. Instead, we face a future of increasing isolation. As the expansion speeds up, more and more galaxies will be carried away from us at speeds faster than light. They will cross a cosmic event horizon and disappear from our view forever. In about 100 billion years, all galaxies outside of our own gravitationally bound local group will have receded beyond our observational reach. Future astronomers in the Milky galaxy will look out into a night sky that is almost completely black and empty, with no evidence that a universe of 2 trillion galaxies ever existed. The story of the Big Bang, of cosmic expansion, and of the grand cosmic web will be lost to them, erased by the relentless work of dark energy. A more extreme, though speculative fate is the Big Rip. If dark energy is not a cosmological constant, but a dynamic field that grows stronger over time, a concept known as phantom energy, the acceleration could become so powerful that it would eventually overcome all the other forces of nature. In the final moments of the universe, this repulsive force would tear apart superclusters, then galaxies, then our solar system. Planets would be ripped from their stars, and then the Earth itself would be torn asunder. In the final fraction of a second, even atoms and their nuclei would be shredded, ending the cosmos not in a cold freeze, but in a violent, universal disintegration. While current data do not favor this scenario, it remains a theoretical possibility, a testament to the terrifying power of the invisible force that governs our cosmic destiny. We stand at the precipice of our knowledge, at the 93 billion light-year edge of the observable universe, contemplating a cosmos whose ultimate fate is governed by an invisible, accelerating force. It would seem that our journey into scale has reached its final, absolute limit. But the most profound and mind-altering concepts in modern cosmology arise when we ask a simple question. What lies beyond the edge? What is the nature of the universe that we cannot see? While we can never answer this with direct observation, our most advanced theories of physics, cosmic inflation, and quantum mechanics point towards an answer that is as spectacular as it is untestable: the multiverse. The idea of a multiverse, a reality composed of numerous parallel universes, is not mere science fiction. It emerges as a natural, almost unavoidable consequence of our best model for the earliest moments of creation: cosmic inflation. Inflation theory proposes that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of hyper-accelerated expansion, growing from a size smaller than a proton to something larger than a grapefruit in an instant. This theory brilliantly explains several key features of our cosmos, such as its large-scale uniformity and its flat geometry. The multiverse enters the picture through a concept called eternal inflation. According to the theory's leading proponents, the quantum field that drove inflation did not decay everywhere at once. Instead, it decayed in certain patches, creating bubble universes like our own, where inflation stopped and a standard Big Bang expansion took over. However, in the vast sea of space-time between these bubbles, inflation continues, and it continues eternally. This eternally inflating background is constantly spawning new bubble universes, each potentially infinite in size, each with its own Big Bang, and each evolving in complete isolation from the others. In this scenario, our entire observable universe, all 2 trillion galaxies, all the vast cosmic web, is just a single, infinitesimal bubble in an infinite frothing ocean of other universes. This cosmic ocean is expanding so rapidly that the distance between the bubbles is growing faster than the speed of light, making any form of travel or communication between them fundamentally impossible. They are separate, causally disconnected realities. This model opens the door to even more bewildering possibilities. The laws of physics as we know them might not be universal. When each bubble universe is born from the quantum foam, the fundamental constants and even the basic forces of nature could crystallize in different ways. In another universe, gravity might be much stronger, preventing galaxies from ever forming. In another, the charge of the electron could be different, making chemistry impossible. The number of spatial dimensions could even vary. The multiverse, in this view, becomes the ultimate cosmic laboratory, a place where every conceivable physical reality is tried out. We, of course, find ourselves in a universe with laws that are conducive to the formation of stars, planets, and life, simply because we couldn't exist to observe it otherwise. This is known as the anthropic principle. A different, though equally mind-bending version of the multiverse arises from the mathematics of an infinite universe. Measurements of the cosmic microwave background suggest that space is geometrically flat. In a flat universe, the simplest and most likely topology is that it extends infinitely in all directions. Our observable universe is just the finite patch we can see. But if the universe is truly infinite and contains a finite number of possible quantum states for matter to be arranged in, then the laws of probability dictate that any given arrangement must eventually repeat. This means that in an infinite universe, there is a finite distance you could travel before you would encounter an exact, atom-for-atom duplicate of our entire 93 billion light-year observable universe. And further on, there would be another, and another, an infinite number of them. In this quilted multiverse, there are infinite versions of you, living out every possible variation of your life. In one, you chose a different path at a critical juncture. In another, you are identical up to this very moment, but will make a different choice in the next. It is a staggering concept, suggesting that all possibilities are not just potential, but are physically realized somewhere in the infinite expanse. A third branch of multiverse theory comes from the many worlds interpretation of quantum mechanics. This idea proposes that every time a quantum measurement is made with a probabilistic outcome, the universe itself splits into multiple branches, one for each possible outcome. In one universe, the particle went left. In another, it went right. Over cosmic time, this constant splitting would create an infinitely branching tree of parallel realities, a near infinite number of Earths and versions of history, all existing simultaneously. While these multiverse theories are deeply compelling and mathematically elegant, they currently sit at the very edge of science, perhaps even beyond it. By their very nature, they are largely untestable. We can never visit another bubble universe or peek into a parallel quantum timeline. However, some scientists are searching for indirect evidence, such as anomalous cold spots in the cosmic microwave background that could be the bruise left behind by a collision with another bubble universe in the distant past. Whether these theories are ever proven or remain in the realm of philosophy, they represent the ultimate conclusion of our journey. They suggest that our entire universe, in all its incomprehensible vastness, might itself be just a single grain of sand on the shore of an infinite cosmic ocean. And so, we arrive at the end of our grand tour. We have journeyed from our home planet, a speck of dust in the vastness of the Milky Way, to the edge of everything we can possibly see, and even beyond into the speculative realm of the infinite. We have seen our galaxy as one of a local family, our family as a suburb of a great cluster, our cluster as a node in a continental supercluster, and our supercluster as a single thread in the grand cosmic web. We have stared into the great voids, counted the 2 trillion galaxies in our cosmic census, and confronted the dark, invisible forces that are accelerating our universe towards a cold and lonely future. The journey reveals a profound and dualistic truth about our place in the cosmos. On one hand, humanity is rendered breathtakingly, almost absurdly, insignificant. We are a fleeting phenomenon on a microscopic rock, orbiting a humdrum star in an unremarkable galaxy, lost in a universe of unfathomable scale and population. Every war we have ever fought, every border we have ever drawn, every moment of triumph and despair has played out on a stage so small it is invisible from even the nearest star. Yet, on the other hand, something truly remarkable has happened on this tiny stage. The universe, through the long, slow process of cosmic and biological evolution, has produced a creature capable of understanding all this. The star stuff that was forged in ancient stellar furnaces has, on this planet, organized itself into conscious beings who can build telescopes, write equations, and comprehend the story of their own cosmic origins. We are the universe's way of knowing itself. The mind that contemplates the cosmos is a part of that cosmos. We are the custodians of cosmic awareness, the fleeting but precious consciousness of a universe that would otherwise be vast, silent, and unobserved. Our journey to understand the scale of reality is not just an intellectual exercise. It is the universe itself waking up.